Alright, now we next look at part C. Part C wants us to calculate the incoming current supply in the phasor and sinusoidal expression format, right? To calculate current, we use Ohm's law. Now, Ohm's law states that the current in the phasor form, let's write I. Current in phasor form is the voltage in phasor form divided by the total impedance. In part B, we calculated E in phasor form as 229.81 at the angle of minus 30 degrees volt. Whole thing divided by the impedance in polar form, because we're going to do a division. So we have 63.246 at the angle of minus 18.435. 10.435. So, alright, so this is the impedance. So divide, we will get we divide this, we'll get 3.634 ampere. The phase angle will be minus 30 degrees minus 18.43. So that gives us minus 11.565 degrees. 565 degrees ampere. Alright, so this is in the phasor form. Now in the sinusoidal expression, we need to convert this back into V peak. Now V peak is this is RMS, so V peak we have to multiply by square root of 2 sine omega t. Now omega t, the frequency all remains the same with voltage, so we can write this 314 t. But this time the phase shift is minus 11.565 degrees. Okay, so this will give me a value of 5.139 sine of 314t minus 11.565 degree ampere. Okay, so that's in the sinusoidal expression. Alright, so that's for part C. I need to calculate the current in phasor form and the current in sinusoidal expression form. Now we next go on to calculating the voltage drop across the resistor, the inductor, and the capacitors. Now we know current, right? So the voltage drop VRT is actually let's put this as phasor form. It's equals to current, the input current in phasor form multiplied by the impedance. So in this case, we have 3.634 at the angle of minus 11.565 degree multiplied by the resistance 60 ohms at the angle of 0 degrees. So that gives me 218.04 at the angle of minus 11.565. Angle, when we multiply, we add them up. Volt. Okay, so that is the voltage drop across the resistor in phasor form. VLT is actually VLT underscore I times, in this case now, is the impedance due to the inductance, right? So I will have 3.6 3.634 angle minus 11.565 degrees, multiplied by the reactance of the inductor is 120, but this time there is a phase shift of plus 90 degrees. So that gives me 436.08 at an angle of minus 11.565 plus 90. That gives me 78.435 degrees volt. And finally, the voltage drop across the capacitor is VC I multiplied ZZC, which is 3.634 at the angle of minus 11.565 multiplied by 140 ohm with an angle of minus 90 degrees. That gives me 508.76 508.76 with an angle of minus 101.565 degrees. Alright, so these are the three voltage drop in the phasor form. Alright, now for part E, we are required to determine the values of the inductors and the capacitors. Now we know that the reactance of the inductor is given as 120 ohms. But this is also equals to omega L. Okay, omega L. Therefore, L is XL over omega, which is 120 divided by omega. We can derive from the sinusoidal waveform is 314. So the inductor value, the inductance value will be about 0.382 Henry. Remember, inductor values are measured in Henry. Similarly, for the capacitor, we are given the reactance of the capacitors as 140 ohm. This is also equivalent to 1 omega C. Therefore, the capacitance is equals to 1 over omega times 140. That's equals to 1 upon 314 times 140. That gives me a capacitance of about 22.7 microfarad. Alright, so we have done part A, part B, part C, part D, and part E. Alright, so for part F of question 1A, what we want to do now is to draw the waveforms of ET and IT. Now, very roughly, we can sketch this out, right? If ET waveform is like this. Now, what happens now is because there is a minus 30 degrees. Now, that means that this whole waveform is shifted, right? Shifted to the right. That means if I were to identify this as the 0 point, the VT will start crossing the 0 point after a lag. Similarly, IT will also be that way. But because IT angle is smaller, IT crosses the 0 point earlier. So how do we convert these degrees into something similar for along the horizontal line? So the first thing I would do is to get 30 degrees. Now minus 30 degrees means what? Minus 30 degrees is the same as 30 degrees over one cycle, which is 360 degrees, multiplied by the total cycle time, so that's 20 milliseconds. So it gives me a lag shift back of about, okay, let's just do a quick calculation. It's about 20 millisecond divided by 12. 1.66 second. This means 1.667 millisecond backwards. Alright. Whereas for minus 11.565 degrees, that's 11.565. I'm gonna put the minus sign there. 360 multiplied by 20 milliseconds. That gives me 11.565 divided by 360 times 20. 0.6425 milliseconds. Right. So now I'm ready to draw my two waveform. First waveform, maximum is 325. Now because it is shift back by 1.667. So if I were to draw something like that, I can just label it, because I need 20, right? So every division I can have 2, 4, 6, 8, 10, 12, 14. Oh, sorry. So here I will have 2, 4, 6, 8, 10. So it's 10, 12, 14, 16, 18, 20. As you see. But because everything is moved back, so I will have, so here's my 20 millisecond. This is my 10 millisecond. So if I move back by 1.66, right? So here is 2, here's 1.66. Somewhere here. So the voltage crossing over will be here, right? Similarly, everything else get pushed back about the same value. So it's about here, and it's about here. So that's the zero crossing point for the voltage waveform. And for the maximum point originally is here, so I get pushed back by 1.66. So push back by 1.66 will be, here is 1.66, so it will be pushed back to somewhere here. 66. So here 5. So somewhere here, okay. So the maximum voltage occur here. Similarly for this, it was originally here, so it gets pushed back to somewhere here. So my maximum voltage the other way, negative way. Okay, so I have marked out the points. So at when it is 0, the values will be somewhere in between. So come down. Okay, so if I were to plot it out, I will draw my sine wave this way. So roughly around here. Sine wave this way. Comes around here. Okay, so this is my ET waveform. Now we look at the current waveform. Now current waveform, what happens now is just displaced back by about 0.64. 0.64. So here is 1. So 0.64 is around here. This is where the current crossover is 0. So if a current crossover there, the current could have done here now is crossover at 0.6 something. So the current crossover is around here. Now it reach a maximum around here. It reach a maximum at okay, 1, 2, 3, 4, 5, right? So originally here I shift back. Okay, so everything shift back. So this will also shift back by original here. Now it shift back here. Slightly ahead of the Right. Current waveform reach a maximum at this point. Okay, and finally it cross back again. It is ahead of this point, so it's about here. Right, so if I were to draw the current waveform will look something like this. Comes down, comes from here, comes down here, goes underneath, comes out here again. So it rises something like that. Okay. So this is IT. Alright, so the two waveform, if you look at this, you can conclude one thing is that the current I, IT leads VT by the angle difference, right? By the angle difference between these two, that's about 18.435 degrees. Okay. So if I were to label this properly, this should be 0.6425 millisecond, whereas this point is 1.667 millisecond. Alright, and here you are. This is because you need to label the so-called the period. The period is here to here. Period T is 20 millisecond. Right, the peak value V peak, I peak, here. Of this question.